Hello. So in this section, we're going to talk about primes and greatest common divisors. So prime numbers have been of interest in math, and in particular number theory, for quite a while. They're interesting. Right? A prime number, it's an integer that is greater than 1. And it's called prime if the only positive factors of that number p are 1 in itself, okay? And a positive integer that's greater than 1 is not prime is called composite. So prime numbers have been of interest historically just because they're interesting. They're special numbers. So from kind of Greek times when they were playing around with math, there's been an attempt to find the prime numbers, larger and larger prime numbers. So that's sort of been a quest for mathematicians to do, and also for computer scientists. Okay, so kind of in the last 300 years especially, and most recently too, kind of this quest for larger and larger prime numbers has been one of interest, and is very applicable today because, as I've mentioned before, prime numbers are very important in encryption and cryptography because it allows systems to be secure if you work with large prime numbers. Now, sort of the encryption is harder to break if it's based on large prime numbers. So a lot of the stuff that we've done in this chapter so far, and we're doing this chapter, it's kind of showing how this is sort of connected together, and prime numbers has a big part of it, but it's sort of kind of in terms of applications to computer science, that's sort of the goal, is that you learn about algorithms that have been developed and are being developed for computers to do arithmetic with really large numbers, in particular with large primes. All right, so this section we're going to learn about prime numbers, prime factorization, the greatest common divisor, the lowest common multiple, and how things are connected in sort of this new language that we're learning with divisibility and mods and congruencies, right? So the fundamental theory of arithmetic says that every integer that's greater than 1 can be written as uniquely as a prime or as a product of two or more primes, where the prime factors are written in order of non-decreasing size. So this is called prime factorization, basically. All right, so we're going to look at some numbers, prime factorization. So let's start with that. Let's look at some numbers and decide whether they're prime or composite, and if they're composite, we're going to break them up into their prime factorizations. All right, so part A, we want to find a prime factorization of 100. All right, so this is not a prime number, so kind of a good method for finding the prime factorization is a factor tree, or you can list. You might have seen this before as, let's break 100 as 2 times 50. That's a prime, you circle it. 50 is 2 times 25. This is a prime. 25 is 5 times 5. They're both primes. So you kind of work through until you kind of break it up into its composition of primes. So you can write 100 as 2 squared times 5 squared. Okay. Let's look at 641. All right, so 641 doesn't divide by 2. Okay, so this is sort of when divisibility rules are useful. It's like if it's even, it divides by 2. If I add all the integers, I get 11. Okay, if you add all the integers and the sum divides by 3, then the whole thing would divide by 3. If the sum is 9, then the whole thing divides by 9. So that's not the case here. So we're going to divide by, I know it doesn't divide by 5. Let's try by 7. Nope. Let's try by 8, 9, 10, 11. Nope. And try by 13. And we're going to try by 15, 17. Nope. By 19. And 23. And what's the next prime number? 27, 29. Okay, so I'm running out of numbers. Okay, so basically, I kept dividing by prime numbers until like my answer was smaller than the number I'm dividing by. So for example, when I divided 641 by 29, I got like 22.1. So sort of all the prime numbers up to there, and when so this number becomes smaller, you're going backwards. You basically you've already sort of used those possibilities, you know. So you run out of choices, and you go, oh, this is prime. All right, let's look at C, 999. Okay, so you can do the factor tree. Sometimes I just sort of do it in one line. I kind of go, well, 999 is 111 times 9, and 111 looks like it divides by 3. So this is 37 times 3, and 9 is 3 times 3. So you don't have to do the whole tree thing. You're basically just going to split it up until you get all primes. So 37 is a prime. The 3 are primes. So I can write this as 3 to the 3 times 37. Okay. Let's look at D. 1024, that looks familiar. I think that's a power of 2. So I've sort of been doing a bit of binary conversions in the last section. You probably recognize this as 2 to the 10. Again, sometimes it's not necessary to go the full factor tree. You can sort of partially do it, things that you know. Along the way, you can break it up to, you don't have to go through all the steps. All right. Okay, so let's talk about trial division and this theorem. If n is a composite integer, then n has a prime divisor less than square root of n. So when I was trying to figure out 641, I kept dividing by prime numbers, okay? And basically, after I got to a certain point, I stopped because it's like, oh, I ran out of choices. So this is basically what this says. So it says that if n is a compositive integer, then n is going to have a prime divisor less than square root of n. Because square root of n times square root of n makes the number itself, right? So if you kind of go by contradiction and say, oh, it has to have a divisor bigger than square root of n, then that's not going to work, because if the prime divisor bigger than the square root of n, then this has to be less than square root of n, but basically that means that one of the divisor has to be less than square root of n. So you kind of can prove this by contradiction. So I won't go through proof, just sort of like an overview. So I showed that 101 is prime using trial division. You want to take the square root of 101, which is approximately 10. Okay, so 10 point something, just a little bit over 10. And then we want to go through all the prime numbers up to 10 and check them. So basically, you're going to divide by 2, you're going to divide by 3, we're going to divide by 5. We're going to divide by 7. And I run out of primes. Okay, so because it doesn't divide by any of these, and you've sort of reached that upper bound for what the prime divisor could be, then you can say this is prime. Okay, so that's trial division, just kind of brute force, giving an upper limit for what the divisor could be by taking the square root of the number, and then checking all the primes up to that upper bound. Okay, so this is, if you're programming, this is a sort of works okay for small primes, not so great for large primes, because it will take hundreds and thousands of years for a computer to kind of go through a trial division if we're talking about the kind of large primes that are useful in encryption. Okay, so let's look at this trial division again. So let's find the prime factorization of 7007. Okay, so I see that if I take the square root of 7007, I get 83.7 approximately, it's rounded. All right, so I need to check all the prime numbers up to 83 before I give up. Okay, so let's go with, all right, so it doesn't divide by 2. It doesn't divide by 3. It doesn't divide by 5. But it probably divides by 7. Okay, so 7007 divided by 7 gives me 1001. All right, so 7007 is 7 times 1001. So now you start the process again. You go, well, let's take the square root of 1001. And that's approximately 31.6. Sure, that shouldn't be there. 31.6. There you go. And then we're going to do trial division with this one. It doesn't divide by 2. It doesn't divide by 3. It does not divide by 5. Does it divide by 7? Probably not. It does, actually. It does divide by 7. 143. All right, so 7007 is 7 times 7 times 143. All right, so let's take 143. We'll find the upper bound for that. Square root of that is 11.9 something, 11.6 approximately. So we do trial division. It doesn't divide by 2. It doesn't divide by 3. It doesn't divide by 5. 43 divided by 7. Nope. Doesn't divide by 7. And I think it divides by 11 though. No, it doesn't. 143 divided by 11. It looks like, oh yeah, it does divide by 11. Divides by 11. It looks like an 11 number. Division by 11, you can check, like for 3-digit ones, if these two add up to the middle one, then it divides by 11. All right, so we get 7 times that 7 times 11 times 13, and we can write this as 7 squared times 11 times 13. All right, so this is trial division. You can see it's a bit brute force. For small number, a computer would do this really quick. But you sort of, we try to be more clever about it, both by doing it by hand and by programming a computer. So try to come up with some algorithms that are a little bit more efficient. All right. All right, so somewhere in the quest of finding larger and larger primes, mathematicians proved a few theorems. So this is probably one of the first ones. They're fairly significant, is that there are actually an infinite number of primes. Okay, so you don't run out of them. Okay, so we're going to outline a proof here. And we're going to do this by contradiction, indirect proof. So by contradiction, we are assuming that there are a finite number of primes. Let me get a little bit finer. So assume a finite number of primes. Okay, and let's list them. They're going to be P1, P2, Pn. Pn is my largest prime here, and then I run out, they stop. Okay, so this is my assumption here. All right. So we're going to let a number Q be the product P1, P2 through Pn plus 1. Okay, so we're going to form this new number Q. And according to the fundamental theorem of algebra, we have two cases. Case one is that Q is prime, and case two is that Q is composite. So those are the only two choices for integers, positive integers, according to the fundamental theorem of algebra. Now in this case, case one, if Q is prime, this is a contradiction. Okay, so this is the contradiction to what I assumed here, because if we assume that a finite number of primes, these are written in increasing order, like Pn is my largest one. So if I'm saying that Q is prime, Q is definitely bigger than this largest prime, because I'm multiplying all of them together and I'm adding 1. So this would be a contradiction. Okay, so we're going to move to the second case and see what happens in the second case. Okay, so what if Q is composite? Okay, so if Q is composite, then that means that Q can be written as the product of two or more primes. Okay, so Q is equal to the product of two or more primes. Okay, and since P1, P2, Pn are the only primes in our world, right, then one of those P's right here has to divide into Q. Okay, so that means that one of the primes above, call it pk, has to divide into Q. Okay, so pk has to divide into Q. All right, so let's go up here. Now let's rewrite. We're going to rewrite this expression here by subtracting this product from both sides. Okay, so I'm going to rewrite this as Q minus P1, P2, Pn equals 1. Okay, so I just subtracted that term from both sides. Okay, so since pk divides into Q and pk divides into P1, P2, Pn, right? This has to be true because pk is one of the primes on this list. Then pk has to divide in the difference between Q and P1, P2, Pn. I think this is one of the theorems that we proved in the last section, and it kind of also makes intuitive sense if pk divides into two numbers, it's also going to divide into the difference between the two numbers, right? But I know from up here that this difference equals to 1. So pk divides into 1. And this is a contradiction, right? This is a contradiction because the only thing that divides into 1 is 1, okay? So pk is a prime number, which means it's bigger than 1, so this can't happen. Okay, so because I got contradictions in the only possible cases for q is prime, automatically leads us to a contradiction. Q is composite also leads us to a contradiction. That means that our assumption that there's a finite number of primes is incorrect. So this means that there are an infinite number of primes. All right, cool.